Section 19.2 is on balancing redox reactions, and we balanced a simple redox reaction in section 19.1, but a lot of redox reactions are actually very complicated and difficult to balance. This is because of a couple of reasons. First of all, there are some reactants that may not be included, like H plus ions, OH minus ions, and water. And they're not listed because the reaction could be balanced differently depending on whether it's under acidic or basic conditions. Second is that you have a hidden constraint, and that's that the number of electrons transferred need to be balanced. Electrons don't show up in the completed chemical equation, and so that's kind of a hidden variable that needs to be balanced, even if all of the atoms balance the same number of irons on both sides, for example. That doesn't necessarily mean that the number of electrons will be balanced, and so that's something you need to keep track of separately. And lastly, and this kind of happens naturally, but redox reactions will need to balance their charges as well. The total overall charge, maybe on the reactant side, everything adds up to be 3+. Well, everything on the product side will have to end up being 3+ charge as well, or 0 and 0, or negative whatever and negative whatever. The charge will need to be balanced. And so there are 7 steps for balancing redox reactions. Hold on a sec, we'll pull those up. So the first is to just balance all of your elements that are not hydrogen or oxygen. Balance them as usual, so you have the same number of atoms on each side. And then you're going to want to look at the oxidation numbers, identify what has been oxidized and by how many electrons, what has been reduced and by how many electrons. And then you'll want to modify the coefficients in order to balance those electron transfers. So if you need to have more of one reactant in order to balance the number of electrons, then that's what we'll go ahead and do. And then we'll balance the oxygen atoms by adding water molecules to whichever side they need to be on in order to make the balancing work. And then finally we'll balance the hydrogen atoms by adding H plus ions if we're in acidic conditions. And we'll address basic conditions in a little bit. The last step is just to verify that all the atoms are in the right, and the overall charge are balanced. That should happen if you balance properly all on its own. So let's look at an example. So S2O3 minus plus Cl2 gas. And I'm going to leave some space here because we may have either H plus or water that is also going to be on the reactant side. So I'm going to leave a little bit of room there. And then that's going to form sulfate, SO4, 2 minus, aqueous, and Cl minus. Okay, so our first step is to balance any of the non-oxygen and hydrogen elements. For example, I've got 2 sulfurs over here and only 1 here, so let's put a 2 right there. And then I've got 2 chlorines over here and only 1 over there, so let's put a 2 right there. Next we're going to assign oxidation numbers. So oxygen, when it's in a compound, is always going to be -2. There are 3 of them, so that's a total of -6. This ion has an overall charge of 2 minus, and so there should be a +4 in there that is counterbalancing the oxygen, and it is divided between 2 sulfurs, so each of them is just a +2. The chlorine here is easy, that's 0. The chloride is also easy, I'll just put that in right away, -1. And then we'll do the same sort of analysis here. We've got 2 minus for the oxygen, oops, -2 for the oxygen. There are 4 of them, so that's -8. And so there should be a +8 to counterbalance it. And there's only 1 sulfur, so it has all of that +8 oxidation number. what we see is that the sulfur has gone from +2 to +8, and so it has been oxidized. Oxidation is losing electrons, and so its oxidation number increased as it lost those negatively charged electrons, and it looked like there was a total of 6 electrons that the sulfur lost. And then the chlorine went from a 0, yeah, that's fine. The chlorine went from a 0 to a -1, so it was reduced. It gained electrons, and each chlorine gained 1 electron. Now, there are 2 sulfurs in each of these S2O3, so I guess that's a total really of 12 electrons. And there are 2 chlorines, each of them gained 1 electron, so that's a total of 2 electrons. But if we want to balance these, obviously we're not there yet. We'll need to have 6 times as many chlorine ions. Hold up. I made a terrible mistake. Sorry, I should have looked at my notes earlier. This sulfate ion is not neutral, and so if it has a total sum of oxidation numbers from the oxygen of -8, the sulfur is going to be a +6 in order to make the overall charge be 2-. And that's going to change all of our numbers here as well. So we're going to have actually only 4 electrons for each sulfur that are lost as it goes from a +2 to +6. And with the 2 sulfurs, that's going to give me a total of 8 electrons. Okay, I apologize for that. And so it's a matter of balancing the 2 electrons gained from the reduction of each Cl2 molecule against the 8 electrons lost through the oxidation of each S2O3 ion. And in order to balance those, we're going to need to have 4 chlorine molecules. And we're going to need then 8 chloride ions. So we've modified those coefficients to balance the electron exchange. Now we'll balance any missing oxygen atoms by adding water. And we've got only 3 oxygens on this side, but we have 4 times 2 is a total of 8 oxygens on the product side. So we have a deficit of 5 oxygens. We'll add 5 H2O on the reactant side. And then we're going to balance any missing hydrogen atoms with H+ ions. Now we didn't have any hydrogens before, but we just added 10 over here, so we're going to have to balance that with 10 H+ ions there. And if we look at this, the overall charge on the left side is 2-. The overall charge on the right side is also going to be 2- when you consider 8- from the chlorine, and then 2- from each of the sulfates is going to be a total of 12-, and then the 10 H+'s give us 2- overall. So the charge does indeed balance. So let's look at another one. Let's do Cr2O7. Cr2O7 aqueous plus Sn2+ aqueous and that's going to form Cr3+ aqueous plus SnO2, and that is a solid. So let's back up here and show the process. First 3 steps are to balance any non-oxygen or hydrogen elements. Well, I've got 2 chromiums on the left. I'll need 2 chromiums on the right. Tin seems balanced just fine. we'll get oxidation numbers. This one's easy, that's a 2 plus. Chromium is 3 plus. Tin over here is going to be 4 plus because it is counterbalancing the 2 oxygens to make a neutral ionic compound. And then the chromium over here, oops, this should be a 2 minus dichromate ion. Sorry, I missed that charge. So oxygen is -2. There are 7 of them, so that's a total of -14. The overall charge is 2 minus, so we should have a positive 12 divided between the 2 chromiums is positive 6. And now let's see what's happened as we go from chromium to Cr3 plus. It goes from positive 6 to positive 3, so it has been reduced by 3 electrons. And there's actually 2 chromiums right now, so that's a total of 6 electrons. And the tin has gone from 2 plus to 4 plus. And so that has been oxidized by 2 electrons. In order to balance those, we need the least common multiple between 6 and 2. So let me actually scroll down a bit. So we're going to modify those coefficients to balance the electron exchange. I'm going to need 3 tins in order to make that 3 times 2 is equal to 6 electrons. And now I'm going to balance any missing oxygens. So I've got 7 oxygens on the left, and 2 times 3 is 6 oxygens on the right. So I'm going to need a water. And now balancing the hydrogens, I just added 2 hydrogens, so I'm going to add 2 H plus aqueous over there. And it just fits in screen. So now we have balanced this chemical equation. When we balance in basic conditions, the first step is to balance it as if it were an acid. And then we're going to add 3 additional steps that sort of modify it and make it into a base. So I'm going to kind of erase all of my annotations here, and we'll balance both of these equations now under basic conditions. Okay, I think we've cleaned that up. So the first step is for each H plus ion, you're going to add an OH minus ion to both sides. So here we have 10 H pluses. We'll add 10 OH minuses to both sides. And then the next step is to combine any H pluses and OH minuses that appear on the same side to form waters. So these 10 H pluses and 10 OH minuses are actually going to be 10 waters after we combine them. And then the last step is to cancel out any water that appears on both sides. For example, we have 5 waters here and 10 waters there. Well, we can eliminate those all together, and this becomes just 5 waters. In the end, I'll rewrite the balanced equation. We have S2O3 2 minus aqueous plus 4 Cl2 gas plus 10 hydroxide ions. And that is going to form 2 sulfates plus 8 chlorides and 5 H2O liquid. If we do the same thing down here, so every H plus is going to give an OH minus to both sides. So plus 2 OH minus plus 2 OH minus. The H plus and the OH minus that appear on the same side are going to combine, and so they give us 2 H2O liquid. And then we can cancel out any waters that appear on both sides. So we've got 1 water over here, we'll eliminate that, and then we'll have only the 1 water on the reactant side. So our final balanced equation is H2O plus dichromate plus 3 tin 2 ions is going to yield 2 chromium 3 plus ions plus 3 tin 4 oxides plus 2 hydroxides. And that is how you balance under basic conditions.